There's a lot of people on this list that I do not recognize by name, which is fine. We are PA Consulting. We organize these meetups. Started years ago, just as an internal, let's meet up and have fun, dive deep into technology, the mathematics behind AI. And then we started to invite clients, and then we thought, well, because this field is built on open source, how can we give back to the open source community, to the public community? And this is one of our attempts to be friendly with our the giants that we build on. So today, indeed, Pandas. What if your data frame? Oh, sorry. What if your data is actually a Pandas data frame? Couple of weeks ago, we had a session on not everything is a data frame, but what if? What if it is a data frame? Then and not just a simple one, but a really big one. What are the little things you can do to make it more speedy? And Jelle has prepared a nice little talk about that. We will be sharing the recording. We will be sharing any of the code that Jelle will use during the session. But without further ado, Jelle, take it away.
Yeah, thank you, Willem, and thank you, Susanne, for the introduction. Jelle Dikker, working as a data science consultant at PA Consulting. I'm living in Amsterdam, based with PA. I'm working from the Utrecht office, also in the Netherlands. And I think we're gonna spend today. I'm not sure if we will, if we're gonna spend the full 2 hours talking about speeding up your Pandas workflow. So it might be actually a little bit less. Let's get started. I would say the beginning. In the beginning, there's a few questions that I prepared for you with Mentimeter. So there's a little bit of interaction, and later on I will share a number of examples. Yeah, so as I said, this talk is all about speeding up your Pandas workflow, and probably you're all aware of what Pandas is. So it's a library that sits on top of the Python language and that you can use for all kinds of data manipulation tasks. Now, what I would like to do now is to ask you a few questions. So I'm gonna just share the link in the chat. And I would like to start with the question why Pandas is sometimes your favorite tool for the job at hand. Great. So I see easy coming back quite a few times. Everything is a data frame. I couldn't agree more. Python, versatile, import CSV well, works well with Jupyter. It is what I learned. Yeah. And it has lots of built-in functions. Great. Thank you all for the contributions. Yeah, I think there can be a number of reasons why you want to use Pandas. For me, it's also often it is what I'm used to, and it's maybe the easy way to do something. Now let's move on to the next question. Let's see, how do I do this? Yeah, and there's also sometimes these cases, and you should now also be able to fill out the next question. These cases that you do not really want to use pandas, but you're somehow forced to, or you have to. Yeah, I see, for instance, people saying maybe the previous work was done in Python, or so you're sort of stuck. You're not able to change that, of course. You don't want to work. You don't want to change all the previous work. I see a few times that it works so great if you combine it with machine learning. So you can use, for instance, scikit-learn for that. And I see, is there something else? No, not really. But let's move on. Thanks a lot for your inputs. I think there can be a lot of different reasons why you want to use pandas, and this, for me, it often comes down to the functionality, or why you sometimes have to use pandas, and that is also has something to do with maybe, for instance, with the type of environment you're working on. Maybe the client you're working for has Python and pandas installed, but is not necessarily ready to switch to using some other language or technology. So these can all be reasons why you want to work with pandas. Now I'm gonna share the slides again. So here we are. Yeah, and the question is, of course, no matter if you just want to use pandas and Python, or if you're somehow forced to do it, how can we speed it up? Because obviously there are other technologies, let's say Spark, which are much faster, but they lack, let's say, they lack a number of the functionalities that you have if you use pandas, maybe combined with scikit-learn. So in order to, so this is what I would like to talk to you about today. And in order to speed your pandas workflows up, there's actually two things I would like to share with you. First of all, I want to introduce cProfile, which is a tool that you can use to profile your code and to get an idea of where you actually spent the time on. Second thing is I want to share a number of, let's say, common pandas tips and tricks that you can use to speed up your pandas workflow. So cProfile. cProfile is a Python profiler. And as you can read on the right, it allows for deterministic profiling of Python programs. So basically, it collects statistics about how often and how long various parts of your program are being executed. And of course, afterwards, what you can do is you can use this type of information to make improvements. Now I created a really nice function in order to show you what cProfile can do and how you can speed up your Pandas workflow. The function, what it does, it opens a CSV file, my weatherstation.csv. Then it's actually turns the CSV file into a data frame. It adds a column which turns the timestamp into a date time. Then it adjusts the timestamp because the clock of our sensor has been was 1 hour off. And then it uses this, let's say, corrected timestamp, which has been adjusted by an hour, in order to determine what time of the day the measurement was. So, and in order to do this, we actually take the timestamp, call the apply function, and then we actually apply this function. So what that function does, it takes the hour attribute from the datetime object and then just sees if it's between 0 and 6, that must be in the night, and then if it's between 6, if it's between 6 and 11, it's in the morning, etc., etc. Now the final step is to first of all calculate the mean temperature per day part, so the mean temperature for the morning, mean temperature for the afternoon, etc. And then it determines the difference with this, so the difference between the temperature that was measured and then the mean temperature per day part. Now, when all of this is done, we write it again to CSV so that another analyst can work with this data. Do we have any questions so far? Is this function clear to everyone? Oh. Yeah, I assume there's no questions. That's good. Let's move on. Now, cProfile. Let's say the most easy way to work with cProfile and to get a profile is actually just done in 2 lines. Importing cProfile, then using cProfile run, you can actually evaluate a string. So as you see, what you see here is a string, which then under the hood gets executed as Python code. And this generates, what this does is it then gives you an overview of all these functions that have been called. And now I would like to explain what it actually means, what you see here, because you see number of calls, you see total time, etc. So the number of calls is the number of times this certain function was called. The total time is the time spent in that particular function without taking into account the calls to other functions. And the cumulative time is actually the time spent in that function, including calls to other functions. So what you see is that there's often, this is of course, let's say a nested execution, right? So typically with Pandas, you start with some higher level Pandas function, and these functions in turn make calls to lower level, normally NumPy functions. And in this report, you see those all, you see all of those. You see lower level functions, you see higher level functions. So it can be a little bit difficult to make sense of this. Oh yeah, and you also get the time per call. So what you see here, for instance, is we perform this get daypart function 100,000 times. Now I know that my data frame was, where's the million? I know that my data frame was anyways consisting of 1,000,000 rows. So apparently this get daypart function is performed one time for every row in my data frame. And you see that altogether, this takes half a second. And that is per function call. Yeah, round, if you round it, it is 0.00. What else? Yeah, and on the right, you see the file name and then also the line number. So here you see get mean temperature per day part is on the first line of my Python file. Now this string evaluation, I think it works to get a quick result, but sometimes you want a bit more control, especially when you want to get insight in what I just said in the nesting of all these different higher and lower level functions and how that relates to each other, because it can be a bit difficult to make sense of that just looking at this list. Plus, maybe you just, I personally don't like it that it is a string in this previous example. And this especially gets a little bit difficult if there's more, if you actually need to measure more steps. Then it's also nice if you can do multiple lines of code, for instance, and if your IDE highlights them as being Python code. Now, if you want more control and no strings, you can just start a profiler and disable the profiler. Everything in between gets analyzed, gets profiled. Also, what you can do is you can sort. What you get back is stats. And with these stats, you can do all kinds of things in order to understand a little bit better what's happening. For instance, you can just sort them. And especially the cumulative time gives a good impression of how these functions are nested, right? Because if the cumulative time is rather high, and then the total time so the time actually spent in that function is low, then you know that it probably passes it on by calling another function. That's also what we see here. So we see the get mean temperature per day part. Yeah, we spent 37 seconds in there, but only 0.076 seconds in that particular function, and the rest is passed through. Now, what you can also do is sort on total time, and then you get the low-level functions, of course, that where you spend the most time. In our case, we see here this underscore strip time, and I believe that has something to do with converting our date time into the right format. What else? Write CSV rows. Well, that's a function that the write CSV function uses to actually do the write. And yeah, in order to understand this sort of complex nested structure a little bit better, there's also another, there's also some more helpers. First of all, you can strip the directories from the stats to make it a little bit more readable. On the other hand, you're also missing information. And what you can do is you can perform a selection on what you actually want to print. So you perform a selection on, in this case, by using print callees, you perform a selection saying that I just want to have something that starts with list. So I want all my list comprehensions. And And then I only want to have the calls going from this list comprehension. So I've seen in the previous, where was it? In the previous view, I've seen somewhere that here you see that I spend a lot of time in this list comprehension. So I figured it would be a good idea to zoom into that. And how do I do that? I select all the outgoing calls from this list comprehension. So that's this one. And then you see that this list comprehension, that it just make 1 million calls to the method that we discussed before. So these are all tools you can use to understand the output a little bit better. And I think that just looking at one, this is, let's say, a flat list, is often not enough to really understand the flow of your program. Now, what you can also do is, of course, if you want to analyze what your functions are doing, is you can do these kind of things as a decorator if you find it more convenient. And there's also all kinds of tools that visualize this information. Now this is, I believe this project is called PyProf to call tree. And then you can sort of visualize, follow the flow of that particular program. So you see how many calls go from the main to a wrapped function to make request, etc., etc. And especially, I think this is this is not so, doesn't look to me so complex, but especially if you're using, of course, a lot of libraries, that in turn use, so you're most likely using high-level functions that use a lot of different lower-level functions. And this might turn into a huge web of function calls. So that was the introduction on cProfile. Do we have any questions so far?
I don't see any in the chat yet.
Okay, very good. And I assume that everybody understood what I just showed.
Well, I think it's quite cool. I didn't realize that this was a function in Python. This is completely new to me. So thanks for that. And I was just wondering, how much overhead does cProfile actually add to your program? So are you also hampered by cProfile itself?
I haven't tried it out myself, but in the documentation, of course, they say it's not that much overhead. It says reasonable overhead.
Reasonable, okay.
Yeah, and
that sounds reasonable.
Yeah, but we could also try it out later. So Pandas, if there are any more questions, also you could feel free to just interrupt me. That's also fine. Or post a question in the chat and then. Okay, Pandas. So looking at your responses to the Menti, I assume you all know it. So that's great. And I've also seen various reasons why people like to work with Pandas. So I'm happy that that is used also so widely. Now I think in order to make improvements to any type of Pandas workflow, you first need to understand a little bit about what kind of data types Pandas uses. Now, Pandas has, and this is what you see on the left, has their own D types. which can be, for instance, an object which is typically text. It can be integers, floats, datetime, etc. And what you see on the right is the corresponding Python type, as well as NumPy types. And now, what is most, I would say, what is most important to remember from this table is that Pandas often has only one implementation per type. So let's say int 64. And then NumPy has often a lot more different types to choose from. And the cool thing is that with Pandas, you can actually use NumPy types interchangeably. So whereas Pandas would by default always make an integer and int 64, you can actually say, no, I would prefer to have int 16 or uint 32. So by default, it is not super efficient, but it's also not always a problem. I mean, if you just want to try things out, etc., then it's fine to have some overhead and to have a little bit more space, of course. Now I wanted to check out my weather station data. As you can see, our data has 4 columns. It has a timestamp, wind speed, temperature, and wind direction. Now we see that so far, by default, the timestamp has been loaded as an object, so as a string. Wind speed and temperature as integers, and the wind direction also as an object, as a string. Now, if we look back at the table that we just seen, I think there's a number of things that catch my attention. First of all, I don't see any date time. This was represented as an object. Also, I don't see any category, but if I look at the data, it looks to me a little bit like this might indeed be a finite set. So these are things that we can, that we can maybe use. What we also see is the following. So Pandas has a very convenient function which allows you to check out how many, what is the memory usage of a data frame. So Pandas basically reserves space in your memory to make sure that that it can I'd say accommodate all the values that you have in your data frame. Now you see the index is fairly efficient compared to the rest. And now I think it's good to keep this in mind that these are the numbers to start with, and then later on we will see how they change if we change our data types. Now, first of all, what I did was changing this wind direction. You could see that it consisted of west, east, those kind of strings. So we only have 4 of them. Change it into a category. And what you see, this is already nearly an 8-fold improvement. So what actually happens if you turn it into a category is that it saves 2 things. It saves the how to say it reserves some space for the labels. In addition, it reserves some space for the labels as well as for the for the integers that point to these labels. Nevertheless, it's a great improvement. Now, what we've also seen was that these integers, they were all represented as int 64, and yeah, that is a lot of space because obviously, yeah, an int 64 can accommodate really big numbers, and that's maybe not necessary if I look at what the data in our data frame looks like. For instance, the wind speed that we measured was never smaller than 0 and never bigger than 9. And the temperature was never smaller than -11 and bigger than 8. So if we look here to the left, I would think maybe we can use some, yeah, let's say a little bit smaller NumPy data types. Now, if we indeed do so and we change the wind speed and the temperature to an unsigned integer and an integer of 8 bytes, then indeed you see the reserved space changing.
Jelle, we have a comment from Arjen that if you want to know the real memory usage set deep is true. I'm not sure if that's about this one, but can you comment yourself, Arjen?
Can you hear me now?
Yes.
Yeah.
It's easier than typing. Sorry for that. Yeah, if you do your memory usage, then if you have, like, for example, a column that contains strings, then the memory usage will only refer to the pointers that are actually pointing to the actual strings. So it doesn't count the memory of the objects that are actually referred to. So if you want to know the real memory usage of the total data, so not only it's an underlying NumPy array, etc., and it's really hard to explain like this. But an object is actually a 40-byte a pi object, which has a reference to something somewhere else in memory. And if you do memory usage, it will only count all those name references, but it will not count the actual memory that is being used by the object that it is pointing to. Just you can try it out. So if you say memory usage and you say memory usage deep equals true, you will get different numbers.
Yeah, that's
and usually more.
Yeah. So in our case, we changed. Yeah, we changed this object to a category. We've won probably even more.
Yeah, you probably want more because you weren't counting the string values themselves. You were only counting the references to the string values. So you gain more. And as I have the audio right now, when you're downcasting to other numeric types, you could use the PD2 numeric function. It has a downcast function, and so you can automatically say this is an integer, and then it will downcast to int 8 or unsigned int 8 or whatever, because it will automatically check what the smallest representation is that it can use. Just so you know.
Yeah, thanks. Great additions. So remember to use, for the memory usage, use the deep is true. And if you want to convert numeric types, you can also use PD to numeric, and that's a bit less hassle because it automatically checks what is the most appropriate type. Yeah, and what I wanted to show you also is that we changed here 2 columns to an unsigned integer 8 and an integer 8, and then it apparently takes 1,000,000. And what you see here, if you use this categorical type, is that it reserves some space for the yeah, the same space as for a normal integer, and then some space for the labels. And the 204 is what I would assume to be for the labels. All right, let's move on. Now the question is also, of course, if you set manually these these data types, what happens if you would then try to fill your data frame with a bigger value? Let's say so a value that's out of bounds. Yeah, so what I did here is I tried to insert a value which is much bigger, and then you see it doesn't, at least it doesn't result in an error or break your code, but also it automatically changes back again to the other column, and this, I didn't really understand this behavior, but so combining flexibility and speed, maybe what you refer to using PD to numeric would actually that would then be the way to go, to make sure that you have always the best data types. Also, I included a link to Kaggle where there are also people that have written functions that just check the range of your data and then pick the most appropriate size. Okay, so far for the data types. Now I've run a small experiment because an important question is, of course, when do you want to do this conversion? Do you want to do this when you're reading your CSV, or would you like to do this maybe later after reading your CSV, converting it to the types? This is a let's say a reminder of the performance, and I wanted to highlight two things here. So the write CSV rows takes 4.3 seconds, and apparently it does some conversion to different types at some point, which takes 5.5 seconds. Is that correct? Yeah. Now, now the result from this small experiment was that, when you convert to the data types already when you're opening the file, it actually saves 2 seconds in our workflow, and this results from a few small improvements. For instance, writing to CSV is all of a sudden a second faster, and I don't remember. So, and there were a few more that were just very small improvements along the entire pipeline. Now, the strange thing was that in this case, if you would convert the data types after opening the file, that step in itself took quite some time, and that offsetted the wins. So that was not faster. Now we had the data types part. Now there's still a number of other improvements that you could make, and I think the best way to go about this is to just take a look at your function. Where do you spend most time, and then apply the Pareto principle, where you want to focus your efforts on the parts that take the most time, and also, of course, the parts that take the most time and that you somehow reasonably expect that you can still improve on, because some things will inevitably take time. Now what I highlighted here is that in this strip time, apparently, which is this datetime conversion, apparently a lot of time is spent. So that's something we would like to look into. And yeah, one of the easiest ways to do this is to just turn it into a Pandas timestamp when you're reading the file. I did need to change some other parts of the code, but that's rather easy. Now, and that resulted actually in a reduction of around 50%. So we started with 35 seconds, then we got 2 seconds off by changing the data types, and now we actually got 50% off by parsing the date in a bit more efficient manner. So not using a list comprehension and Python's date time anymore, but just converting them all in one go when reading the CSV. Now looking at what remains, I see there's this apply, which still takes quite a lot of time. So apparently we're spending 6 seconds or so out of 15 in this apply. And yeah, so the way it was made up was like this, right? So we take the timestamp column and then just apply this function. Now, what I would like to propose is to change it to a vectorized function. So we use the time to get an idea if the time was in the night, in the morning, afternoon, or evening. So now we're using pd.cut, and this allows you to split data into bins. Now it works only with numeric data, so in order to be able to do this, we first need to extract the hour from the timestamp, and this can again be done with the DT, the date time accessor. So this is a shortcut to get actually date time properties. So let's see what happens. Yeah, we managed to get another 6 seconds off. And now, okay, so we changed data types, we changed the way we're dealing with timestamps. We used a vectorized function instead of the of applying. Now there's one more thing remaining, but before going into the right CSV, I would like to share this with you. So what you see here is, so we just changed basically a loop with the apply function to vectorization. So we use now the Pandas cut function, which is a vectorized function. Now, in general, I would say a normal regular Python loop is the slowest. You can of course also use iteros, which iterates over the rows. And the fastest on this list is vectorization with NumPy, but what you can of course also do is use Python or just C++. So maybe this list should have been a bit longer. So I think this is, if you're thinking about speeding up your Pandas Python code, it's good to keep this list in mind. And of course, always measure. Now, there was one thing left, the toCSV. So what I did is I tried out, and this is maybe a little bit cheating because who knows the requirements. One of the important requirements was to actually deliver the results in a CSV file. And what I did is I changed it into a feather as well as into pickle. Now there are also a lot of blog posts about what data format to use for what type of data, what is the fastest, and a lot of people performed all kinds of elaborate experiments to compare these, because some are a little bit faster when you write them, some are a little bit faster when you read them, and everything of course also depends heavily on what the type of data you have. So if you want to read more about this, there's a lot of things to find online. I just tried pickle and feather and then decided to go with pickle. Yeah, and that means that that in the end, we managed to bring back the execution time of this function from 35 seconds to 2 seconds. So we use smaller data types. We did a little bit smarter date time conversion. We're not using an apply anymore, but we changed it into a vectorized function. And we're now writing to pickle instead of CSV, which is apparently faster. I see also a question in the chat. A few. Yeah. Okay. So the first comment was on if you parse dates with read CSV, there's a day first is true / false. Yeah. Yeah, and I think what you can also do is if you know the format, is just give the format so that Pandas doesn't even have to figure it out. That Pandas doesn't have to figure out the correct date format, but you can just give it in as a string. Or you write a custom date parser. That's also possible. What is the optimization approach when the apply function cannot be changed into a built-in vectorization function? Yeah, then what remains is then maybe you could actually use Siphon or write a C++ function. Because it is true, you're often limited to of course, the type of functions available in either Pandas or NumPy and that are vectorized. Yeah, or Numma. I'm nearly. So nearly done now. Just want to share one slide still with you about that sort of summarizes what you have seen today. So first of all, I would say if you want to go for speed, start profiling so that you know where you actually spend time and resources on. Then what I've showed you today is actually a few ways to speed things up with Pandas. Typically, these things speed it up, but you never know until you measure it. And there's, of course, a lot more that I did not manage to cover today. For instance, as I said, you can use Siphon or call C++ function from within Python. You can also use multiprocessing. And multiprocessing is actually a way to use multiple cores in Python. And I think because Python does not always do this by default. So especially if you have, let's say calculations or tasks that require a lot of computation, so not so much I/O. If you then use multiprocessing, you can get a lot of extra speed. And there's a lot of other topics that I saw Arjen mentioning in the chat number, but probably there's a lot more that is not on this list that it's also worth to read about if you want to speed your Pandas workflows up. But yeah, if there's anyone that still wants to mention a few additions, feel free to do so, and then I think we can have a short conversation about it. And otherwise, if not, I want to thank you already for listening, and Luke, please feel free also to approach me if you have if you find interesting blog posts about these kind of topics. I always love to read that. See tuna being mentioned.
Okay, if there's no further questions or comments, then Jelle, thank you very much. Very useful, and this was even on a very small data set. Imagine what would happen if it's even larger and you even start running out of memory. I like the suggestions. So thanks for those. Obviously, parallelization is the only way to go if it's really big, and then then you're already quite quickly looking at things like PySpark to run things on a cluster. But Jelle, thank you very much. Very insightful, concise. Everyone, thanks for joining today on this beautiful Friday afternoon. We will share obviously the video on our YouTube channel, and we will share the code on our GitHub. But for now, thanks very much, and I wish you a great weekend.
Have a nice weekend.
Thanks, Jelle.